Hello. This class is 12th class, 4th chapter, magnetic effect of electric current, and second session. Here we are going to discuss about the different cases of charge entering a magnetic field. Okay, look at this case. Here the magnetic field and velocity. This is the direction of velocity. This is the magnetic field. So they are in the same direction. So magnetic field and velocity in the same direction means theta is equal to 0. So the force will be equal to QVB sine 0, that is equal to 0. Okay. Now look at this one. The magnetic field is moving like that and the velocity is in the opposite direction. So magnetic field and velocity are mutually, they are anti-parallel. They're anti-parallel. So we can say QVB sine 180. Sine 180 is 0. So again force is equal to 0. So next is the charge rest in a magnetic field. See, this is a magnetic field and the charge is at rest there where the velocity is equal to 0. There is no velocity for the charge and the charge is kept rest in a magnetic field. So the force will be equal to Q into 0 into B sine theta. So that will be equal to 0 only. Next is the case with charge entering at any angle that we already studied in the previous class. The magnetic field and velocity vector is making an angle theta. So the force will be QVB sine theta, where the direction of the force will be equal to QV cross B, isn't it? So to find the direction of the force, you have to apply the right hand rule. See, this is my right hand, but you are seeing it as left hand, that I know. You are seeing it as left hand, but actually it is my right hand. Why? Because while taking the class, I'm writing it on a screen, which is glass screen, and I'm flipping the video. So when I say this is my right hand, you may be seeing it as left hand. So just leave that. So I will apply it here, and in another class, I will give you something which is on the blackboard itself. Without using glass, I will show you what actually happens in blackboard, right? Without flipping, I will show you one another. Now I will just proceed with taking it as my right hand. So this is my right hand. Actually, it is my right hand. I'm a right-hander. Writing on board, what I'm doing it is with right hand. But when I take the flipped video, it becomes left. That's all. So you just take, this is my right hand. So I have to take my right hand and curl, these are fingers, and this is what thumb is. So this is finger and this is thumb. I have to curl my fingers from the direction of V to B. Okay. So I have to curl the fingers from what? V to B. So this is direction of V and this is direction of B. So I have to curl my fingers from V to B. Yeah, I cannot curl my fingers V to B like this. I have to place my fingers like this to curl it from V to B. So that is what the direction of V cross B. This is direction of V cross B, and it is acting into the plane of the board. So the magnetic field, the magnetic force will be acting into the plane of the board. Or I can say it is away from me. That's the best thing. It is away from me. So that is what the force expression for, or the value of force, or the value and direction of the force on a charged particle entering at any angle. Next is the charged particle entering a perpendicular magnetic field. So I make it like into marks. It shows the magnetic field is into the plane. Okay, the magnetic field is into the plane. The magnetic field is into the plane, and that is into the plane. And into the plane magnetic field, the charge is entering perpendicular to it. Just like the magnetic field is into the plane and the charge is entering like this. So they are mutually perpendicular, right? So the magnetic field is acting into the plane and the charge is entering like this. So I have to say in this situation where the magnetic where the charge is entering perpendicular to the magnetic field, force is equal to QVB sine 90, the angle between the magnetic field. This is magnetic field and this is direction of motion of charge, and that is 90. So it is QVB sine 90, it is QVB only. Now there is a new rule known as Fleming's left-hand rule. Fleming's left-hand rule. And Fleming's left-hand rule gives you direction of force on a charge, on a positive charge, entering perpendicular magnetic field. Direction of motion of a direction of force on a positive charge entering perpendicular to magnetic field. So you may ask me, if it is negative charge, then what will we do? I will give you the solution. Again, we have to use the left hand. So this is my left hand. I know you are seeing it as my right hand. What you are seeing is the mirror image. That's all, because I am flipping the video. So this is my left hand. So I have to take my, so please forgive me for this mistake. It is my left hand. That's a technical issue. But you don't worry, I will make it clear. I will make it clear in a whiteboard class how this happens with application of this left hand rule and right hand rule. You just don't worry about it. Let me complete the class now. So you have to take your left hand and take thumb, forefinger and middle finger. Okay, this is middle finger, forefinger and thumb in mutually perpendicular direction. Okay, the law states that it's like this: thumb, forefinger and middle finger of your left hand in mutually perpendicular direction. It says that if this forefinger represents magnetic field and middle finger represents direction of motion of positive charge. Forefinger represents magnetic field, middle finger represents direction of motion of positive charge, then the thumb will give you the force acting on it. Thumb will give you the force acting on it. So what is that? Father, force, mother, magnetic field, and child, current. So father, mother, child. This is my left hand. Don't forget, this is my left hand. So what you have to take is your left hand and three fingers in mutually perpendicular direction. Okay. So before I use in mutually perpendicular direction, I will give you the technique of applying it. Okay. Club all the fingers together first. Open what? Open finger for magnetic field first. So this is the finger for magnetic field, and make it in the direction of the magnetic field. Yeah, it is magnetic field. Now this is magnetic field, right? Now this is your charge motion finger, finger for charge motion, right? So you have to place your left hand, again this is my left hand, again you have to place your left hand in such a way that the middle finger keep the direction of the motion of the positive charge. Yes, then I have to place it like this, right? Once more, this is the direction of the magnetic field. This is only the finger for direction of motion of positive charge. So I have to place my left hand in such a way that the middle finger represents the direction of motion of positive charge. Now you automatically open the thumb. It will give you the direction of the force. So this is the direction of the force. So this direction of force means what? The charge entering here will be experiencing a force which is acting upwards. Like, see, this will be experiencing a force upwards, so it will bend. As it bends, the force will also be bending, right? You got it, like this. It enters, it bends, bends. Yes. So it will be following a path like this. And it is perpendicular to the velocity. The force will be perpendicular to the velocity. Do you know something? Do you know something? If a force is perpendicular to velocity, that type of force you know, actually it is centripetal force. isn't it? So the force here is equal to what? QVB. The force here is QVB, and that force is perpendicular to velocity. A force which is perpendicular to velocity can act as a centripetal force. So this will act as a centripetal force, and it will follow a part of a circular motion in the magnetic field. If the magnetic field is existing everywhere, it will follow circular path, uniform circular motion. It will follow uniform circular motion because the magnetic force acts as the centripetal force. Now here, if there exists only magnetic field in this region, now it will follow the curve of a circle. Okay, it will follow the curve of a circle within that range only, within that field only. Okay, so within this magnetic field, it will follow the path of a circle, where the centripetal force, you know what centripetal force? mv square by r, is given by this magnetic Lorentz force. It is QVB. So square and velocity is cancelled. So you will get radius is equal to mv by qb. So the charged particle entering a magnetic field perpendicular to the magnetic field. Charged particle entering a magnetic field perpendicular to the magnetic field will experience a force, and that force acts as the centripetal force, and it will follow a circular path. And the centripetal force is provided by the magnetic Lorentz force, so R equal to mv by qb. Or also velocity is equal to qbr by m. Okay, if you take again this equation, this radius is equal to mv by qb. See, this mv is what? Momentum. So it can be p by qb. Okay, so that can also be root of 2me by qb, isn't it? Why? You remember the equation, kinetic energy is equal to p square by 2m. Okay, so p square is equal to 2me. So p equal to root of 2me. That is one equation that you studied in first year class. So it can be root of 2me by qb, where E stands for kinetic energy. Now it can be in another form also. If a charged particle is accelerated by a potential difference v volt, if a charged particle is accelerated by a potential difference of v volt, it acquires a kinetic energy qv. You remember that? If a charged particle is accelerated by a potential difference of v volt, it is v volt, it's not velocity, v volt, it acquires a kinetic energy qv. So we have to say the radius can also be written as root of 2m into qv by qb. Remember, it's not velocity, it is potential difference. So I will conclude, a charged particle entering parallel or anti-parallel will not experience any force. Charged particle at rest in the magnetic field will not experience any force. Charged particle entering perpendicular to the magnetic field will experience a force, and that force will act as the centripetal force, and it will follow a circular track of radius mv by qb. And that mv by qb can have different form. mv equal to momentum, momentum equal to root of 2me, and E equal to qv. If a charged particle of charge q is accelerated by a potential difference of v volt, it acquires a kinetic energy qv. So this is what the conclusion is. Again, in between I will say I made a mistake in recording this video, that I told you I was using my right hand, but you were seeing it as left hand. Forgive me, that's a technical mistake, because I'm taking a video which is having a flipping concept, because I'm writing on the glass board. So from glass board I'm shooting. So before I make the video, I have to flip the video, right? So that's why my left hand is turning to right hand and right hand is turning to left hand. That's all. Yes, previously we got the equation for the radius, and that radius is equal to mv by qb. Okay, where the charged particle were having a circular motion in the magnetic field. This is what I gave you. Like in a magnetic field, it follows a circular track. Now, what is the time period of circular motion? What is time period? Time period, for one circular motion, time period will be 2 pi r, which is perimeter by velocity. Distance by velocity, this is what time is. So it is 2 pi r by v. So from here you can see what is r by v. From here you can see r is equal to r by v equal to, from here it is r by v equal to m by qb, isn't it? R by v equal to m by qb. So time period equal to 2 pi r by v. And r by v equal to m by qb. So time period will be equal to 2 pi, instead of r by v I can say m by qb. So what? In a magnetic field, when charged particle is entering perpendicular to the magnetic field, it will be following a circular track. And the time period for that circular track is 2 pi m by qb. Time period of that circular track is 2 pi m by qb. Now frequency, it is what? 1 by time period. 1 by time period is qb by 2 pi m. qb by 2 pi m. And what else is omega, angular velocity. You know what angular velocity is? 2 pi f, isn't it? 2 pi f. So omega is equal to 2 pi. F is frequency, it is qb by 2 pi m. So omega is equal to 2 pi can be cancelled, it will be qb by m. So we got certain relations. What are those relations? One is time period, which is 2 pi m by qb. And frequency is qb by 2 pi m. Omega, angular velocity, is qb by m. In all these equations, there is no v or r. There is no radius or velocity. What it shows? Any charged particle entering in a magnetic field perpendicularly through any radius or any velocity, the time period, frequency, omega will all be same. Or time period, frequency and angular frequency is not depending on radius and velocity. Actually, this is the working principle of cyclotron. We will discuss what is cyclotron in the next class. This is the working principle of cyclotron. Just I am giving you an information. We will be using this particular information to find the value, to explain cyclotron. What is cyclotron? We will explain it in the next class. Okay. Thank you.